We've all been there, sucked into the task at hand, and forgotten about that cup of tea we made earlier. By the time we remember, it's too cold to enjoy. Perhaps this problem is inconsequential, but as eloquently stated by Richard Feynman, no problem is too small or too trivial if we can really do something about it. With this in mind, let's get cracking. Of course, there are simple solutions here. For example, we could set a timer, but this is no fun, so I decided to build a convoluted mechanism that would ring a bell when my beverage was at the right temperature to drink, which is around 55 degrees centigrade. The mechanism is based around a simple scientific principle, and that is thermal expansion. When a material is heated, it will most likely expand, and the amount of expansion for a given temperature difference is dependent on the material, and this is quantified by the thermal expansion coefficient. Here I'm preparing two strips of metal. One strip is titanium and the other is brass. Brass has a larger thermal expansion coefficient than the titanium, which is a phenomenon I will exploit in this video. By riveting the two strips together, their relative strains become coupled. I drill the strips and machine some rivets to achieve this. The resulting structure is referred to as a bimetallic strip. As the strip is heated, the brass expands more than the titanium due to its larger thermal expansion coefficient, and the strip has no choice but to bend. The larger the temperature difference, the more the strip bends. In effect, we have a mechanical thermometer, and this is how I intend to measure the temperature of my tea. Before I start machining the rest of the mechanism though, I need to know roughly how much I expect the strip to bend, which can be calculated with this equation. The curvature is a function of not only the thermal expansion coefficients and the temperature change, but also the thicknesses and the moduli of the constituent materials. Once the curvature has been ascertained, geometrical calculations tell us how this relates to tip deflection. Using materials I had on hand, we were able to achieve a theoretical deflection of around 3 mm for the expected temperature change. When I gently heat up the bimetallic strip with a blowtorch, you can see it deflects. Interestingly, although the brass has a larger thermal expansion coefficient than the titanium, you can see that the strip initially bends away from the flame. This is because I'm initially heating the titanium, and we get a thermal gradient across the thickness of the strip. Okay, so the bimetallic strip works nicely, but we need to fix it to the rest of the mechanism, so I get to work on making a brass fitting to be riveted to the bottom of the strip. Regular viewers of our channel may notice the watchmaker's lathe I'm using here is not my usual machine. This machine will ultimately replace the other lathe, and I'm currently working on restoring it. Although it currently looks a bit manky, it's actually a very accurate piece of kit. I will show some of the restoration process in a future video once it's all finished. To show the bimetallic strip working when submerged, I filled 2 small cups with water. The orange cup is filled with hot water and the blue one is filled with cold water. When I submerge the strip in the hot water, you can see it clearly deflects away from the centre line. This sanity check gives me the confidence I need to proceed on to the next stage. Here I'm working on the fitting which will be riveted to the other side of the bimetallic strip. This fitting will accept a probe that will then interface with the triggering mechanism. For these small rivets, I'm using commercially pure titanium wire, which I find provides just the right material properties. The material is soft enough to plastically deform with a hammer during the riveting process, but still strong enough to securely fix the components together. So that's all the components relating to the bimetallic strip now finished, and it's time to get to work preparing a block of brass to which the mechanism sub-assemblies will branch from. I've designed this block to attach to the rim of the mug. Here I'm using the rotary table to machine a curved groove in the block, which matches the curvature of the mug. I made the groove wider than necessary to accommodate a range of different mugs. Achieving a good solid attachment to the mug was initially more of a challenge than I expected. I intended to make a thumb screw that would pull the block up against the inside of the mug, but as you can see here, the inside of the mug is actually curved, providing a poor register for the block. Instead, I had to pull the block up against the outside of the mug, which is vertical and straight. To do this, I made a hooked component that pulled against the inside of the mug when the thumb screw was tightened. Of course, we could have positioned the thumb screw on the inside of the mug, but I think that would have just been a bit too fiddly to use. Before I move on to the hooked component, I drill and tap the block for the bimetallic strip fixing point and round off the top of the block in the lathe to make it a bit more aesthetically pleasing. I now move on to machining the hooked component from square bar. Material choice is always an aspect that requires consideration, especially in cases involving food or drinks. I'm making the whole mechanism exclusively from brass, stainless steel and titanium due to their corrosion resistance, and while titanium and stainless steel are definitely food safe, brass is a bit more arguable, and I would tend to avoid brass in a commercial product that comes into contact with food or drinks. For most of the mechanism I used CZ121 and 120, which contain 2 and 3% lead, but for the bimetallic strip, which is submerged in the drink, I avoided leaded alloys. Ideally, we would replace the brass with stainless steel in the bimetallic strip, which has a similar thermal expansion coefficient to brass, but I just didn't have any on hand. The female thread to accept the thumb screw is fabricated from a separate component, which is then glued into the hook. Next, it's time to work on the thumb screw. I wanted the device to be easy to fit to the mug without needing any tools, so I opted to knurl the thumb screw, allowing easy tightening between the thumb and index finger. There are various methods of achieving a knurl, and to be honest, they can be a bit hit or miss on a lightweight machine. Here I use a cut knurling approach, which removes metal, as opposed to the more popular form knurling approach. Both methods have certain advantages and disadvantages, but for this instance, cut knurling is a good approach. Cut knurling requires the work to be concentric, so I machine the outside in situ. The knurling tool needs to be set to the right diameter to make sure the clearance angles are correct, and then the tool is just fed in. To be honest, this knurl didn't turn out quite perfect, but I decided it was good enough, so moved on to screw cutting the thread. On a Myford with a quick change gearbox, cutting metric threads is easy by replacing a single gear in the train. When set up properly, screw cutting external threads like this is nearly as quick as using a die, and the result is much better because the thread is perfectly straight and can be machined to fit. At the start of the video, I mentioned the goal was to ring a bell when the beverage was at the correct temperature. We considered various approaches to ring a bell, for example a gravity swung hammer, but Hazel suggested using a ball bearing. I loved this idea and got to work implementing it straight away. We would love to hear other ideas in the comments, but remember the challenge here is cleanly impacting the bell once and without damping the bell's vibrations. For example, a swinging hammer would need to be caught and held clear of the bell after the rebound. Added to this, the bimetallic strip is very thin, and therefore it's not very stiff, so the triggering mechanism needs to be actuated with very little force. Here I machine a tilting ramp, much like a seesaw. The idea is the ball bearing will roll down the ramp and onto the bell when the ramp is tilted. I will balance the ramp so only the slightest force is required to tilt it. I make a forked component that sits beneath the ramp to prevent it from tilting too far in either direction. To machine the rounded section of the fork, I used the rotary milling and dividing attachment I made for the new watchmaker's lathe. Now I start to work on the ramp support pillar. This will screw into the main block to support a horizontal rod, which the ramp will pivot about. I am making the pillar from two pieces that will screw together, which will then sandwich the forked ramp stop. Here I show cutting the thread with a die. Using a die holder in the lathe tailstock provides an alternative to screw cutting for non-critical applications. I start with the upper component, which is turned and cross-drilled to accept the horizontal rod. The lower part of the pillar is a simple turning job, so I made this off camera. The bell itself is turned from 40mm diameter brass bar. Traditionally, bells are curved to encourage certain modes of vibration. In fact, bell making is a complex and fascinating process. Usually they are cast from a special bronze alloy and carefully tuned such that the partial frequencies that comprise the overall sound are correctly related to each other. This is out of scope for this video, so I opted for a simple machined design with an overall conical shape. From an acoustic perspective, this is far from optimal, but will work well enough here. As I approach the final thickness, the bell starts to resonate. I carefully choose the spindle speed to reduce this resonance during machining. To face off the top of the bell after parting off, I use a 6-jaw chuck to hold it. These watchmakers' 6-jaw chucks are great for holding thin sections without deforming the workpiece. There's just one last component to make before we can start on the assembly, and that is the part that catches the ball once it's bounced off the bell. I start with machining a simple dish. I begin by facing off a length of brass bar and start a recess with a milling cutter. Unlike a drill bit, the milling cutter produces a flat bottomed hole, which makes it easier to finish the recess off with a boring tool. To attach the dish to the rest of the structure, I make a beam which I then silver solder to the dish. To achieve a good solder joint, I apply flux to reduce oxidization as the metal is heated. An oxy-fuel blowtorch like this gets the metal to the correct temperature for soldering very quickly. This is around 700 degrees centigrade. The soldering itself is very quick. In fact, the cleanup is the most time-consuming part of this process. With all the components finished, it's time to see how they all go together, starting with the bimetallic strip. The strip is bolted to the main block via a cranked rod. The crank moves the bimetallic strip closer to the centre of the mug, where the beverage temperature is more stable. This should improve the repeatability of the temperature measurements. The smaller cranked rod at the top of the bimetallic strip is designed to engage with the ball bearing ramp. The 2-part pillar is then screwed together and the ramp is fitted to the pivot rod. You may notice that I've reduced the length of one of the prongs on the forked component. This is to clear the ramp tilting mechanism, and because the design is improvised, I initially overlooked this. To hold the ramp in position, I machined 2 grub screw collars. These 2 sub-assemblies can now be attached together. This is the bell support pillar. The cross hole accepts an L-shaped rod which supports the bell and dish. Here I make the L-shaped rod by heating some stainless steel and bending it in the vise. The tapped hole in the bell support pillar that intersects the cross hole is multi-purposed. It accepts both a secret grub screw to hold the L-shaped rod in place and the bolt to attach the bell to the dish. The eagle-eyed among you may have noticed I originally tapped the hole in the top of the bell, but I since changed my mind on how the bell was attached to the mechanism, so I drilled it out. When I drop the bearing onto the bell, it rings nicely. But we do get some extra noise from the ball landing in the dish. Additionally, the ball sometimes bounced out of the dish. These issues were solved with a magnet and a foam pad to catch the ball and absorb any noise from the ball landing. Fitting it to the mug is straightforward. The hook is slotted onto the rim, followed by the mechanism. The thumb screw is then tightened. To prime it, the ball is lifted from the dish into the ramp, but this must be done after the beverage has been made or poured into the mug. I spent some time off camera finalising the assembly, adjusting the mechanism and calibrating it, so now it's ready to test. You can see from the time lapse that the bell rings when the water temperature gets to 54 degrees centigrade, which is correct for my taste. To change the triggering temperature, the screw beneath the ramp can be adjusted. Thanks for watching. If you enjoyed this video, please subscribe for more in the future.